everyone. Hi. My name is Arian Karbasi, and we are here for EE classifiers and regression. I'm joined by my TAs in the room. We have William over here and Simon over there in the back. It's Wednesday, where it's been kind of a long couple days, but we're going to try and have some fun with classification and regression. So on the agenda, I'd like to, before we actually dive into examples in Earth Engine, actually talk about what classification, regression, and machine learning are. I know that's going to be review for a lot of you guys over here, but it'll help us ground ourselves in the examples later on, just to have a brief overview so we can discuss what are these things. So after that, we're going to do an example of supervised classification in Earth Engine, and I'll talk about what supervised and unsupervised is. We're going to do a regression example, and we're going to do an unsupervised classification example. So to kind of dive into the box a little bit, when a lot of people think about machine learning, what's in their minds, what they think is you have input, there's a black box, and there's output. That's all they know. So we're going to try and peel back what is in that black box just a little bit. So machine learning is simply an approach to making a lot of small decisions. So things like, is this email spam, yes or no? Or how much should I bid on this auction item? The right side would be an example of regression, where you're predicting a quantity, and the left side is an example of classification, where you're predicting different classes, 1, 2, 3, or yes and no in this case. Another good example would be, is this pixel urban, water, or vegetation, which we'll do in our examples later on. So the actual approach to how we get to that point is very similar to traditional programming. So you always have information, you have some code or a recipe that produces an answer. So when you talk about traditional programming, you have a software engineer sitting there writing the different rules for how you get from point A to point B. And then they produce the answer. When you talk about machine learning, on the other hand, you start on the other end. So you start from your inputs and outputs, and there's some magic that happens. We'll talk a little bit about the magic that actually produces the recipe, and now we have our ML model. And that's the major difference from how we get to the two. So before I go further, I'm just going to kind of define what supervised and unsupervised learning are. When we talk about supervised, it's all of your classes, all of your output classes. So I know at the end of this stage, I want my model to spit out 1, 2, and 3, or yes and no, or urban, water, and vegetation. When you talk about unsupervised, you don't know what your classes are. You're asking the model to say, tell me what my groups are. I don't know what they are, whether there's 4 of them or 5 of them. With unsupervised learning, it's a great way to do exploratory analysis of your data, where you don't really know what it might look like. But those are the major differences. With supervised, you have to kind of tell it, give it some training data, which we'll talk about later. And then regression, like I said, is predicting a quantity and not a class. So it would be good for predicting things like temperature modeling or predicting biomass or something like that. So the very first thing you always want to do when you're trying to build a problem, build a classifier, is what are my outputs going to be? It might be tempting to sometimes start with your inputs, but you really want to start with your outputs, because that might result in slightly different inputs later on. So let's start with a simple example. Let's assume I want to classify my wines. I want to know whether or not I like a specific bottle of wine, and I'll start with my outputs, yes or no. Do I like this wine? Do I not like this bottle of wine? And then what you're going to want to do is identify some useful inputs. So this step can be sometimes difficult when you're in the real world, but in this case, we're just going to do age and review score. Those are the only 2 things that are going to define whether or not I like a bottle of wine. So let's assume I've already tasted 100 bottles of wine, and I've jotted down whether I like them or not, and I've jotted down the age and review score of the bottle of wine. So that's going to be my training data. And the next thing that's going to happen after I have my 100 bottles of wine is probably the most important step, which is splitting your model, splitting your data. So you have your training set, and then you have something called your validation and test set. So the importance of that is, if you train on the entire model, then you have no way of testing your model later on your entire data set. So if you then test with some of the wines that were already in your training set, your model's probably going to get it right, because you already told it the right answer. So you want to have some way of validating. So with the validation set, you're kind of doing quick iterations, soft intervals, trying to see how good your training set is, and you're fitting it to that. So then you have a test set, which you might want to think of it as the final exam. You save it for like the final test when you're like comparing your models, and that's a good way of seeing how well it's done. Otherwise, if you just have your training and validation set, you might overfit to those things, and your model will be very good at getting things that look like your training and validation set, and very bad at predicting things that look like your test set. So let's say this is what our data inputs look like. Where does a machine learning algorithm actually come in? In this case, you might imagine drawing a simple line, right? That is actually a machine learning algorithm. It's called a support vector machine. And the difficulty comes in on where you draw that line. So that's what the algorithm decides. So there's not going to go into the stats of that. That's not what kind of course this is. But deciding where to draw that line is the algorithm. And that can be very difficult sometimes. And that can really highlight the importance of getting good training data, because where that line is drawn depends on the training data. If you imagine in this wine example, if the training data had nothing that was aged greater than 8 years, then all our data would be kind of clumped on the left side, and the line drawn would be a little different, so that when a wine came up later on that was aged 8 years, it might classify it in the wrong bucket. Maybe, maybe not, but it might. So you're going to train your solution on that training data. There's different algorithms. There's support vector machines, there's decision trees, there's neural networks, but all of them do the same thing. They all segment your data in a way that when new data comes in, it asks which box you're in. So in the support vector machine example, this is our model. That's all it is. If it's in the red box, I like the wine. If it's in the blue box, I do not like the wine. So when a new data point comes in, we know how to classify that, and that's what the classifier does. A decision tree might segment it differently. It might create this as the model. They're both different ways of looking at it. And then when a new thing comes in, it's going to say, I don't like that bottle of wine. So it's important to decide which one's better. So in this case, let's say we take the validation set that we've tucked aside, we didn't train on it, and we test our accuracy. We see that the support vector machine was 100%. The decision tree was 75%. So obviously, for this specific use case, maybe the support vector machine is better. Or maybe if you want to use the decision tree, maybe we needed better data to like make the decision tree make better decisions later on. So that was just kind of brief, high-level overview of peeling back that box a little bit. Before I go further, does anyone have any questions on that? Okay, great. So going to talk about some of the limitations of our classifiers in Earth Engine specifically. So we are good for about 100 megabytes of training data. You will get request to large errors if you go above that. So for about 100 bands per point, that's about 200,000 points. Not bad, but not perfect for some use cases. If you need more, you would use TensorFlow. Your feature collection cannot be sparse, so your data set, let's say in the wine example, you couldn't have some points that didn't have the review score in it. Every point needs to have all inputs classified in it. It cannot be a sparse feature set. I think what we do is drop the actual point in that case from the training of the model. And we're good for a generally small number of classes if you're doing supervised learning. I don't know what exactly that number is, but it's not like 10,000 or 1,000. You want, say, 100 or 5, you know, something like that. So what we're going to do is we're going to dive into an example, and we're going to do a live demo. I encourage you, if you want to, you can follow along by copying that down. I'll wait while people copy it. I've already written out most of the code in the examples over there. I don't encourage you to write out too much because you might kind of lose track of what I'm doing. Yeah, maybe if you could put on the whiteboard, that would be.
The link, I think, is also in the breakout session page under the description.
Yeah, because the slides are there.
Oh, okay, great. So if you
just go to the description for this.
Great,
this
perfect. Yeah, and on the left side, under Reader, you should see simple classifier. So if you go to the supervised example, is the one we're going to start with. So I'm going to do a risky thing, and we're going to do a live demo and see how that works out. So can anyone read that? Yep. Okay, great. Okay, so now that we are machine learning experts, we're going to start from where we need to start, which is I would like to do a land cover classification, which is what is a common problem in GIS. And I toyed with the idea of letting the group decide what land we classify, but that is a little too live for my taste, I think. So we're gonna do urban, vegetation, and water, and we're gonna pick an area in San Francisco, a little region in San Francisco to do. So that is our outputs. We've identified our outputs. Those are the three we're gonna have. And let's think of some inputs. For the simplicity of this, we're gonna use a Landsat image, Landsat 8. But for your feature vector, you can add other things that are not part of the Landsat 8 bands. You can add elevation data. Let's say that plays into your land classification. Just different information from different satellites or different data sets that you might have. But in this case, we're only going to use the Landsat 8 raw image. And I'm going to cheat just a little bit. And this is the center that I'm picking, which is, all this is some area in San Francisco that I care to do. And the other cheat part, we're going to define the bands that we care about. So these are going to be our inputs. So you guys, if you're following along in the example, this should already be there. Then we don't care about clouds, so what we're going to do is we're going to create a cloud-free image. So we're going to use one of our algorithms for that, which we have a simple composite algorithm, Landsat. And what we're going to do is we're going to filter it for the last year. I'm going to rename this Landsat 8. Okay, that's fun. Dates, so let's go for the last year. And let me know at any point if I'm typing too fast or you can't keep up. I had some people last session tell me that I was going a little too fast. And we're going to want as float equals true because we are going to preserve the calculated number so we can actually see this is somewhat of an unimportant detail, so we can actually see the image. And then finally, we are going to add this layer to our image, to our map, bands we care about, the RGB bands. And 2, I'm going to specify max. And we're going to call this our unclassified image. Okay, so running that, what we should see is our Landsat composite. Great. So this is what we're going to classify, and this is the urban vegetation and water we're going to classify. So we need to get training data. In Earth Engine, there's quite a few ways you can get training data. You can sample from existing data sets. You can import a collection you already own, and an existing data set that already has pre-classified those things. You can sample from that. Those are generally pretty good ways of doing that, and we'll talk about that a little bit later. The way we're going to do now is not recommended, but it's a little more fun, and it's going to highlight some of the pitfalls of actually having bad training data and what that might do to your classification. So what we are going to do is just hand classify and draw some points on the map and define what looks like urban, what looks like vegetation, and what looks like water. So the way to do that is you're going to go onto your map. We're going to draw some polygons. So we're going to add a couple layers. So you're going to have to do this if you're following along. I did not add the layers in the examples, so you could have fun adding it yourself. So we're going to start with urban. And you're going to specify that to be a feature collection because that's the data type that feeds into the training model. And you're going to add a property. And this is what's being classified. So in this case, it's going to be a type 0. And then vegetation is going to be type 1, water is going to be type 2. So urban, we have our urban. And then let's do our vegetation. Same thing, except this one is class 1. And finally, water, feature collection, and this time it's going to be type 2. So now the fun part, let's actually draw some things. So let's start with urban. And I'm just going to use this little area, I think this would be good, this little area of Soma to classify as urban. You can pick a different area if you want, but we're going to use that. So that's our urban area. And then vegetation, let's use Golden Gate Park, which I hope some of you are already screaming inside. That's not going to be a great truth data for what is vegetation, but we're going to do it anyways. And then for water, let's just pick somewhere in the bay over here. Cool. Okay. So we, in theory, now have our data points for what is urban, what is vegetation, and what is water. These are 3 separate feature collections now, so what we're going to need to do is create, merge them together, so let's do that. Does everyone follow along so far? What's happening, why we're doing it? Okay. So we're just going to merge the collections, so we're going to do urban.merge, vegetation.merge, water. So just to show you what this merged collection looks like, we see that it is a simple feature and it has one property. It has land cover, right? So this is not enough to train on. There's nothing in there. There's only water. What we want is to get the band information from Landsat, B2 to B11, minus some bands in between, and actually get those in this collection so that the training model can actually know what water looks like. So the way you're going to do that is something called sample regions. So what that does is you're going to take basically all the data points in your collection, and then you're going to sample points from the Landsat image to get those bands into the feature collection. So that's going to be our training data. So we're going to take our cloud-free image, we're going to select the bands that we care about, and we are going to sample regions. So this would be a good way to, in other cases, get some training data. And what sample regions takes, you're going to pass it a collection. In this case, it's just our merged collection. So you're saying from this collection, I want to sample regions from my main image, which is the cloud-free image. And you're telling it which property you want kind of propagated down. So in this case, we just care about land cover. And you're going to give it a scale. So this is our training data. And just so you guys can see, you can actually see how many data points we have, and also we can kind of take a look at what it is. So, oh, Earth engine capacity exceeded. That is fun. Let's see. Okay, well, we have 2,100 training points. I'm actually going to make the water data just a little bit smaller. I want us to not have lag issues. Okay. Let's run it again. Okay, Earth engine capacity exceeded still. So we have about 1,000 training points, not bad. And this is what the feature looked like before sample regions. We only had land cover. And then after sample regions, we should have all of our properties. So we have the bands, information over there, and what was the classification. So this is our truth data, this is our training data, and this is what we're going to feed into the classifier. Hopefully I don't get capacity. Okay, cool. So the next step is to actually create our classifier. So now that we have training data, we're going to create the classifier and we're going to train it on that. So the way you're going to do that is pretty simple. We have an EE.classifier, and there's multiple different classification algorithms in here, we talked about decision trees, support vector machines, so you can do SVMs. We're going to use something called random forest for this example for a couple reasons. Random forest generally does a pretty good job. Random forest is a decision tree algorithm, except what it does is it runs many decision trees and not one, and it kind of does a voting to decide which decision tree gets to decide what was the classification. And then I'm not choosing support vector machines because they are sometimes a little bit hard and finicky to get right, so there's a little bit more dials you might have to spin. It will, for a simple example like this, will probably just work, but I'm just going to use random forest. Another note about random forest, we have good defaults for almost all of our classifiers except random forest. So if you remember, random forest is many decision trees. Our default for the number of decision trees for random forest is 1, which defeats the purpose of random forest. So let's pick something like 10 in this example. And again, for this, you don't want to go crazy. Don't pick like a million trees because your thing won't run. Then you're going to call .train. And what the train takes is we're going to pass in the set of features. So in this case, our training data. So this is the 1,000 points that have the truth data in it. The class property. So this is what we want to predict. So in this case, it is land cover, which we added the property earlier. And the input properties, which is just our bands. Okay. So this is the classifier. And we've trained it, and now what's left is to actually classify our image and see what San Francisco looks like with this simple training data. So we are going to create our classified image. So we're going to select the bands again, and we're just going to call .classify and pass in the classifier that we've built. That's all. That's all you do. And in theory, we now have a classified image. So let's add that to the layer as well. We're going to specify min and max. So in this case, we're going to do 0 to 2 because those are the we have 3 classes. Land cover 0 to 3 or 0 to 2, so we're going to do that. And let's specify a palette. So let's pick red for urban, blue or green for vegetation, and blue for water. And let's also give this a name. Okay. So in theory, we have a classified image. Before I press run, how do we think we did? This is the training data. We've trained on some water in the bay, some place in Soma, and Golden Gate Park. Good, bad. Let's try it out. Okay, no errors. That's already a good sign. We should, in theory, I think I did. Let's hide our classified image. Oh, things are happening. Okay. Oh, all right. It didn't do a horrible job so far. It got Golden Gate Park really well. I wonder why. It did some urban areas over there. Obviously, the world is a little more complicated than urban water and vegetation. It did horribly in the ocean over there. We see that it classified what is obviously the ocean as vegetation. So why do you think that happened? We had bad training data, right? We picked some polygons in some simple areas and said, this is what the rest of the world looks like. So good training data is one of the most important things for doing any type of classification. Sometimes it's hard to see visually when you've gone wrong, right? So we can look at this and say, okay, some areas in San Francisco look good. We obviously, this water area in Alameda, we did not do well at all. And the bay or the ocean, we did horribly. You can't always tell that, right? So you need to test your algorithm. You need to actually get a quantifiable way of knowing, did I do good or did I do bad, right? Looking at an image is not always as easy. So one of the ways you can do that in Earth Engine is with a confusion matrix. What that does is it takes the training points that you had, puts them back in the classifier, and compares what you said it was and what the classifier said it was, and if it got it right. So you should already realize that's really a horrible way of doing validation, because you're just putting the training points back in. Of course, it's going to be really good at those training points. but we're going to do it anyways and see what we get. And the way you do that is you specify the confusion matrix. This is called resubstitution accuracy. And you're going to ask for the accuracy. So let's run that again. Okay, we got 1. We got 100%, right? We should be done now. We can leave. We don't need to do any more land cover classification. Obviously, that's wrong because all this really does is show how homogeneous your data was, right? If I had picked an area that was covering both urban and water, and I called that water, then maybe my classifier would have been a little confused when I went to reclassify the things. But humans are very good at picking homogeneous data, so all of the points that it said was water was actually water, and so on and so forth. So this is not a good way of testing your model. It's a good way of testing how homogeneous your data was, which is not what you want. I am going to just quickly change the order of this so we can see our classification every time we run. So what's another thing we didn't do that I said was very important early on, which was I said split your data, right? So we didn't do that. We took all of our training data and we just threw it in the classifier. So let's split our data. One way you can split your data is by adding a random column. All this does is it takes takes the bounds and adds a column called random between 0 and 1. That's it. So from that, we can create our validation set. And does everyone follow along so far? Good. Okay. From that, we can create our validation set, and we are going to filter from this. Filter. And we're basically saying anything less than, let's tuck away 20% of our data for training. So where the random column is less than 20%, is less than 0.2. And then similarly, let's make our training where anything is greater than or equal to 0.2. So now we have a validation set and a training set. We should, in theory, when we're testing, do a little better. So the way we're actually going to validate this is we are going to run our validation set and we're going to classify it. We're going to do the same thing. We're going to pass in the classifier, and this time we're going to ask for an error matrix. And the reason we can ask for an error matrix is because the validation set already has the truth data in it. It already says what is correct. So when we go to classify it, we can say, how did that compare? How did that compare to what was true and what the classifier got? So we're going to ask for the accuracy again.
So can you describe a little bit more about the differences between an error matrix and a confusion matrix?
The confusion matrix takes the training data and it puts that back, the training data that the classifier was classified with, and it just dumps the entire training set back into the classifier. It records what it got, and it compares it to what the training data said was true. So that's all your training data. The validation set was not thrown into the classifier. So when we were training our model, because we split our model up here, split our data up here, the model was trained on 80% of the data, and it was validated, it's going to be validated on 20% of the data. So the reason that is better for testing is because those points that are being classified, the classifier has not seen before, right? They're new data points. And that's a better method for being like, okay, is this correct? Because those data points will have slightly different makeup than what we've trained with, and that's a good way of seeing, did we train with good data, and did our classifier do a good job? Already, we should see that even what we're doing here is bad, and as you'll see, because the data points we've taken are from a polygon. They're from a homogeneous polygon. So one small area of Soma is going to look very similar to another area of Soma, but not Berkeley maybe, right? And that's, we want to get training data from there. I think I did this last time too. What did I do? Oh, yeah. So when you actually ask for the error matrix, you have to ask it which two fields you're comparing. So in this case, we're comparing land cover and whatever classification the classifier threw out, which was just called, it just calls it classification. So we're saying compare these two things. our validation set has land cover. What we classified was called classification. So now we're only training with 907 points, and we still got 1. So again, that's because we have very homogeneous training data, and still not a good way to test. And we might be fooled into thinking we have a good model over here, when clearly, visually, we do not. Okay, so let's try one more thing, okay? The thing we're going to try is specifying new validation data from a different location and seeing how that did. So in theory, that should do a little worse, right? So let's try it. Let us add 3 new layers, and we're going to call them urban validation. We're going to do the same thing. Land cover is going. Yep. Then the other one you're going to call vegetation validation. And finally, water validation. So let's draw some new points. And we're going to pick some different areas this time. Let's try to do, let's say this area of Berkeley has some validation data for urban. Vegetation, let's pick a different area. Let's pick, say, this area of Marin. And for water, because I'm cheating a little, I already know that we did horribly in the ocean. Let's pick some validation data over here. So we're going to have to do the same thing because right now the validation data is just a set of points. So we need to merge them together. And let's comment out this stuff over here. We're not going to split in that way. And we are going to do the same thing that we did before, which is sample from the regions to actually get the data we need to throw into the validation. So, where's our sample regions? Here we go. Okay. So we have different validation data now, and we're doing the same thing. We're classifying. This should be a little better because we're not sampling from this homogeneous location that we've already set as water. It's still not good because we're choosing it. We're not totally randomly sampling, and let's say our model did a little bit better than it, in the ocean, we might still be choosing biased locations. But let's try it anyways and see what we get. Hopefully Earth Engine doesn't blow up. This is the woes of doing a live demo. Oh, look, it's going to do horribly in the water over there. Okay, I'm going to cheat a little again. This should be a little faster. We can ignore what this is for now. Okay, ooh, 44%. Wow. Looks like our model is a little bit worse than we originally thought. And this is why testing and validating and splitting and getting good training and getting good test data is very, very important. We were able to see visually why it was so bad. Might not always be able to, so you need to test. We only got 44%. That is not good. Oh, what just happened? I ran it again. Okay. So what can we do to improve? So one thing we should do is get better training data. Right? This is before you go and deal with the dials of actually how you're changing the model, because we have a lot of dials and specifying what type of random forest you do, specifying a lot of the options for support vector machines. You should almost always look at your data first. It's probably your data's fault. So in our case, we chose bad data, so why don't we go and just add more data and see how we did. So let's go to urban. I'm going to turn this off. And let's just add a little bit more data. So we're just going to draw some points this time for urban. We're going to say this is urban areas. We're not going to be too accurate, but we're going to do okay over here. Let's do the same thing for vegetation. For vegetation, let's just pick some areas over here. Pick some areas in the Presidio, maybe down here. So we're doing a little bit better. We're a little bit more random. We're kind of just picking in different locations now. And we're kind of giving our model a better idea for what vegetation looks like. It looks like more than just Golden Gate Park, at least as far as San Francisco is concerned. And water, let's help it out a lot here and say actually what you thought was vegetation is actually water. I also screwed up this little area of Alameda, I'm pretty sure. So let's add some more points here. You can see I'm not being very accurate here. So we've added more points. We've improved our training data. So let's see how we do now. This is going to be fun. I'm eager. I think we're going to do a little bit better this time, I hope. Oh, Earth Engine. Oh, here we go. Okay, 92%. We did a lot better. And our water looks a little bit better over there. Hopefully we got the ocean. Yep. Our ocean improved. Our classification improved. Our little water of Alameda improved. There's still some areas for improvement, as we can see. But it overall did a pretty good job, given how little effort we put into it. So get good training data, get good tests. So this validation collection is still not perfect. Like I said, we were the ones that chose it. What I'd like to do is bring in a test collection, like I said, from a third-party location. Let me just find the name of it, which I have lost. Give me 1 second. Okay, so what I'm going to bring in is I'm going to bring in a test collection. So this is from a third-party location. This is someone else on our team, not me, has done some hand classifications as well. And we are going to use that to do our test collection. So I'm going to do the same thing. And this is just coming in from a demo we have. It's called Demo Land Cover Labels. Okay. And we're going to do the same thing. So in theory, this test collection is a lot better. Someone else picked it, kind of more randomly chosen, and this would be a lot better at telling us whether or not our model was good or our model was bad. So let's do this. And we are going to do the same thing. Okay. Let's try it again, see how our model did on randomly chosen data, or more random. 93, about the same. So it's not perfect, but this kind of just wanted to go over the pitfalls, how we can improve our training data, and sort of do better when we're classifying an image. So these are the things you should always be constantly thinking about when you're writing classifiers, whether it be in Earth Engine or somewhere else. So was anyone able to get a classified image following along? Yeah? Great. So that's my example for supervised classification. Before I open it up for questions if anyone wants to ask. I'm just going to go through real quick some of the common errors that we have in Earth Engine.
So it sounds like what you're trying to do is to add a do the classification where each feature vector is all the values over time. So one way to do that would be, in fact, to flatten your image collection down to a single image with one band per time sample, and then draw samples from that to classify. There are other ways. What classification actually works on are features, and it's just that the sampling turns, takes points out of images and turns each point into a feature. So however you build up those features is up to you. But one way to do it would be to, as you say, make the image into make the image collection into a single image where each pixel is all the time values.
So common pitfalls that you'll probably hit each one of these if you're trying classification. You can get out of memory. So this usually happens when the tile you're dealing with is too large. So if you're sampling from an image, you're sampling from a tile in Earth Engine. Each tile is, say, 1,000 by 1,000 with a lot of bands. That can sometimes be too much for us to handle. One way you can solve that is the sample function takes tile scale. So you're saying to reduce the tile scale, that comes at the cost of computation time because now you have more tiles. Each tile has has to go out to a different server, which might result in a computation timed out. If you have a computation timed out, there's really not much you can do but try and kind of reduce the amount of data you're actually classifying, or change your training data in some way. You could.
It can actually help that if your computation is timing out interactively, it may work if you run it in batch.
Yeah.
So if
you can always run things in batch.
Because the timeouts are much longer in that, so you can try doing an export of that. Now the problem is that you've now gone from a less than a minute recycle like Arian was doing to it could be tens of minutes or hours to get a result back, because you're doing it in a much slower batch process.
Yep. The other thing you can get is requests too large. This happens when you have too much training data. Like I said, we only can do about 100 megabytes because that's what we're sending to our classifiers. The other thing that can happen when you get requests too large is the model that comes back can actually also be too large. So a good example is if you have a really bad training point and you're making a decision tree, and each node of the decision tree only satisfies, say, 5 points, and you have 1 million points. Now you have a very deep tree, and that's coming back. And if you're doing random forest, you might have 10 very deep trees or 100 very deep trees, and that'll also break our limit. And usually if you're getting that and the model coming back is too large, probably means your training data is bad to begin with. But what you could do is specify on, for example, on any of our decision tree algorithms, you have something called minimum leaf population. So you're telling it, I want each node to have at least this many points. That reduces the accuracy of your model a little bit, but then maybe you won't get request timed out. You should probably look at your data first if that's ever happening. So I actually forgot to talk about an important part, which I was going to, which is good ways to sample data. We did bad ways to sample data. I didn't do any good ways to sample data. So one good way is to take pre-classified data. So there's a lot of data sets in Earth Engine. So you can take pre-classified data and sample from that. So I'm going to show you a couple ways to do that real quick. So we can use Modis, for example. Modis has a land cover classification. You see one of the bands they have is LC type. Their land cover types are a lot better than ours, obviously. They have a lot more variety than just urban water and vegetation, although maybe all you care about is urban water and vegetation. But what you can do is import the model that you care about. Let's call this Modis, the collection that you care about. And then we have different sampling functions in Earth Engine. So So what you could do is a straight sample. So if we were to create, for example, take this. So let's just select the one band we care about. what we're going to do is we're going to add the bands of modus. In this case, it's just the land cover mapping. Right, so now our cloud-free image, the Landsat image, has the land cover type at that pixel and all the Landsat bands. So that's our training data, right? So from that, we're going to sample a certain number of points. And what sample takes is a number of pixels. So you're saying how many pixels you're going to sample. So let's, for the sake of this, do 10. Takes a seed. So the seed basically says how we're going, if anyone doesn't know what a seed is, basically says how we're going to actually choose the random number of elements. So if I run this piece of code with seed 0, when it randomly samples 10 points, it's going to pick the same 10 points every time, right? This would actually be a really good way to get a validation set. You could sample for 0 with a seed 0, say, to get your training data, then you sample with a seed of 1 to get your validation data. That's really good because it's random, you have no bias in this, you're kind of just relying on someone else's classification. Is probably a lot better than just hand classifying on a map. So you pass in a seed and then scale. So that's one way to do a sample. So this is going to sample 10 points from this modus image and send it back as training data. What you might want is to make sure that you have a certain number of points for each class, right? Because maybe you get a little unlucky and you end up with 8 points for vegetation and only 1 for water and urban. So what you could do is called a stratified sample. So it's very simple, but very similar. We're going to do the same thing. We're going to add the bands of modus, the collection that we have. And then this time you're going to pass in a number of points. Don't know why we didn't name them the same thing. And what this is saying, it's a little different. You're saying sample 10 points for each class type. Yeah, you're saying sample 10 points for each class type. And you actually need to give it a geometry in this case, which I forgot to do in the other one as well. Sorry about that. So you would be doing the same thing. You'd add a layer. You need to tell it where to sample from. So obviously we're doing San Francisco, so we can pick some region in San Francisco, tell it to sample from here. Same thing here. You pass it a region, pass in the geometry that we created, scale. But then the difference is you can also override certain classes. So you might care more about water or something else. You might say, I want this number of points from this class and this number of points from this class. So you can say, well, you actually have to pass it the class band that you care about, which in this case is LC type 1, and then overrides. So I'm saying for classes 1 and 2, I want, say, for class 1, I want only 5 points. I don't want 10 points. And for class 2, I want 50 points. I don't want 10 points. So stratified sample is a good way to have a little bit more control over how your sample works. In a lot of cases, I won't say most, but I would say you usually will probably want stratified sample depending on what you're doing, at least if you want to get good training data. So those are the two better ways to get training data, to bring them in. Of course, another way would be to literally get some data from the field and import that as a feature collection. That would be a good way to do it as well. So that is my supervised classification example. Does anyone have questions on that or want clarifications?
When you use the stratified sample,
Yeah.
it should be stratified
Oh,
sample.
yeah.
Oh, sorry.
Oops.
It should be stratified sample
Yep. You
or
are
something
correct.
like that, I guess.
Yep. That was a mistake. It's a live demo woes. So, any questions on that? Nope.
We're catching you up.
Hmm?
We are trying to catch you up.
Okay, I can wait a few minutes if people want to kind of type out and catch up.
So that's not actually a confusion matrix. What are we?
A confusion.
So we're calling confusion matrix, but then what are we? Sorry, so we're calling calculating the confusion matrix, but we're only reporting is that the overall accuracy
Is this from
derived
earlier?
from
Is
the?
this in relation to the sampling we just did, or just?
Oh, further up. Sorry.
So where are you looking?
Oh, so sorry. It's confusion matrix dot accuracy.
Yes.
Right.
Yes. So the confusion matrix doesn't return the accuracy. It just returns the matrice of what the result was and what you told me the truth was.
So that should have been a 3x3 matrix if we just return the confusion matrix.
Yeah. Cool. You can print that out and look at it. You can do other things with it if you want to do other calculations over. But we give you a few functions. One of them is accuracy, which it just calculates the accuracy. The other thing that actually came up yesterday that I want to talk about, a limitation, is we do not have ways in Earth Engine to easily do cross-validation of your data. So for anyone that doesn't know what that is, cross-validation is just taking your training set and splitting it up into k sets, k-fold cross-validation, taking one of those sets to be your validation data, and then k minus one of them to be your training data, and then iterating and trying different versions of k. So that's a good way of testing the robustness of your model to see if it's actually good on different randomly chosen training sets. We cannot do that in Earth Engine. People that do that just code up their own method to do it in a loop. People ask for it. I don't know if we're going to prioritize it, maybe. But that's something we can't do either. So, if there are no further questions, how are we doing for time? So I'm going to do the other two examples. I'm not going to type them out in the interest of time. And I'd like to jump into the clustering example. So going back to what we had, right? We have our inputs, just as an example of what clustering does. Classification will segment your graph and see which area you're in. Clustering, so this is what the method that we use to do unsupervised classification, is it kind of looks at your data and just says what things look like they should go together. So it literally does something like this. It's a lot more complicated than drawing two circles, I promise. But that's what clustering does, and it's a really good way, like I said, of doing exploratory analysis. And if you don't know what your data looks like, you don't know how many classes I have or what things look like. It's a good way of just kind of very quickly getting a response. So we'll see how that might look. So if we go through a clustering example, we're going to start from the same place. The methodology, even though we're doing something different, is very much the same, except in this case, we're not going to have any truth data because we don't need to tell it any truth data. Same thing, we're going to create a Landsat composite, and what we are going to do is to create our training data. I'd like to go back to San Francisco.
What was that shortcut you just used to uncomment?
What? Oh,
Control forward.
yeah. You hold Control or Command or whatever you're at, and then /. It's Command on Mac. Yeah. If you learned nothing else today and you learned that, that's great. Saves a lot of time. Yeah. Instead of going to each line and all right. We can leave now. We're done. Okay.
That's cool. Thank you.
Okay. We're in a classification course, and that is what we learned. Okay. So.
Sorry.
No, it's okay. This is great. So we're going to do the same thing as we did before. Our training data is just going to be our cloud-free sample, our cloud-free image, and we're going to sample some points from our geometry. In this case, we are going to just pick some reasonable representative set. Let's sample points from here and try and find urban vegetation and water. And we're going to do 5,000 points. And then it's very simple. Because we are not doing any training at all, you use the cluster, the Earth Engine cluster, and we're going to use the Weka k-means clustering algorithm. There's many clustering algorithms in Earth Engine. the one we're going to use is what k-means. It doesn't really matter too much for the purposes of this example. Then you're going to do the same thing. You're going to classify your image, so you're going to call cluster on it instead of classify, because it's clustering them, it's not classifying them. And then we're going to add it to our image and see what that looks like. Just going to hide this. And we're going to give it a random set of colors. So we're saying we think there are 3 clusters, 3 images, 3 groups of data in here. Group them into 3 for me and see what that looks like. And hopefully it will look somewhat similar, actually, to what we classified by hand. We'll see how that works. Looks like our model earlier actually missed this little river over here, so the cluster will probably get that. Come on. Ah, here we go. Cool. So the cluster did its job, and actually it did its job with a lot less hand-holding than we needed to do for the classification. It didn't screw up on the ocean over here. It got this little river that we didn't get in our initial script. So kind of comparing the two, we can see that our models were similar, right? It wasn't that bad. We did a pretty good job for how little effort we put into it. But the clustering, like I said, is a good way to just kind of see what your data might look like. And just for fun, let's say our world was a little bit more complicated, and in fact we had 10 groups of clusters, and see what that looks like. And we should get a little bit more complicated of a map when we do that. And of course we do. And the great thing that we see here is that the ocean does in fact look different than the bay. It clustered them differently, which is why our initial classification screwed up. We took samples only from the bay, and we asked it to classify things in the ocean, and it didn't do it properly. And the cluster shows us that. This might be what you want in some cases, but in some cases you only want water and you want them together. But in some cases you want ocean and bay. Really depends on what you want. So this is an example of clustering, and not much more to say about that. There's not too many dials in Earth Engine.
So the next step, you typically label. You can go in as an expert and label. What would be the method to do that? Or if you wanted to combine clusters.
Yeah.
Sorry, the next step would be to label and possibly combine clusters.
You could do that, yeah, it depends. Well, I would say you wouldn't combine clusters. What you would do is you could maybe look at this. You might have a little bit of pre-knowledge about your data and be like, oh, it did the ocean and the bay differently. Maybe there aren't 10 classes, maybe there are 5, and run it again. Kind of see what you want, and then you can classify things from here. It really depends on what you want to get out of it. Then you can go and hand classify, okay, this little bit is bay, this little bit is ocean, and then start classifying that, and then maybe go in by hand and do a real classifier later on. It's a good way of just seeing what your data looks like. So let's go to regression now. So I'm going to apologize in advance for the regression example because it is a horrible, horrible, horrible model, right? What I'm going to do is I'm going to try to predict temperature based on elevation and only elevation. I'm not going to add any other bands, just elevation for the simplicity of the model. And I'm only going to take training data from Yosemite. So it'll be what the world looks like if everywhere was like Yosemite. If only it was like that. So we're going to start exactly the same way as we did before. We want some outputs. In this case, we want to predict our temperature. And we have some inputs. We have elevation. And we need truth data. So we need some collection that has both the elevation and the temperature. So I'm going to use this Prism data over here. I'm cheating a little bit because this Prism data is already predicted values using a regression model for temperature. And we're sampling this already predicted value to then create another regression model to predict temperature values. You normally don't want to do this, but in some cases it might be okay. My data set for Prism here is only the United States. So maybe you want to use this regression model to sample from to then create a model to predict whether might not be a good one because it's very complicated, but for the sake of the argument, to predict whether in Europe or Africa or somewhere else, based on similar climates. and we have data for the United States, but you don't have data in the location you're trying to predict, might be a good way of creating a model for it. So in this case, this is my temperature data. I'm going to take my elevation data from ALOS, and then we're just going to have to create a truth image, and simply, like I said, we just need something that has both the elevation bands and the temperature bands. So we're going to call add data on our elevation data, add bands on our elevation data. And then we're going to use sample like we talked about before. So we have an image, and we need to sample some data points from it. And what I'm going to do here, actually, is go to Yosemite. Where is Yosemite? Here we go. And draw some area that I want sample points from. So I'm going to pick some good representative set, so something that's hopefully close to zero elevation, and something that is close to higher elevation, because Yosemite Valley is very tall, parts of it. So that's our training data, and just to show, I want to show the correlation. We'll have a little chart, and let's run that before I actually do anything else. I did this yesterday too. Okay. I did exactly the same place. Yeah. Just to show you guys that, in fact, temperature is affected by elevation. We can see pretty clearly that as we go higher, the temperature goes down. And we're going to create a regression model based on this data. So the only difference in how you do it is, so we're going to use CART for this one, just to show that we can use different algorithms. We could have used random forest as well. CART is just another decision tree algorithm. And this time you're going to set the output mode to regression. You're telling it to predict a quantity, not a value. And we're training it, and the class property we're predicting is the temperature max, which is what's in there, and the input property is elevation. That's it. And then we're going to do the same thing. We're going to classify and display. So this is not going to look like a beautiful image, unfortunately, but all we've really done with this model is find mountains. Surprise, mountains are colder than flat areas. So this is kind of the regression model of the United States. A lot of the United States is in the same elevation. A lot of the United States is in the same elevation. So our model is predicting that it's going to have the same temperature all over because it's not considering other things. We might have wanted to add longitude, for example, to this model and various other things that would help us predict. But because we've only added elevation, everywhere in the world that's at the same elevation is the same temperature. And we've also done a good job of finding mountains and the Swiss Alps and, you know, the Himalayan mountains over here. So that's kind of a good example of what regression can do using a very, very bad model that I apologize for again.
There's a method you can call on the resultant classifier that will dump out some amount of information.
Yeah. That you could calculate from.
But it's a decision tree regression is not actually doing a linear regression at all. It's essentially carving up the input space into regions and predicting a constant value for each one. So
it's not quite the same as linear regression. SVM would be a little closer to what that would do because it's drawing a line through the data. But even then, it's not the same. We have ways of doing linear fits and linear regression in Earth Engine that are not using classifiers. They're called linear fit and linear regression, and we have our docs. We have docs for that. But those are generally for linear regression, and the regression models you can do with multiple different input variables, which we probably should have done for our temperature model over here. All right, so I think that's all I have for examples and telling you guys about classification and regression. Do you have any further questions?